السلام عليكم ورحمة الله وبركاته. أهلا وسهلا بكم في المحاضرة الثالثة. المحاضرة راح تكون إن شاء الله عن sequence alignment and edit distance. في المحاضرة الماضية تكلمنا عن كيف نعمل indexing, seeding لgenomic sequences عشان نلاقيهم في مثلا مجموعة كبيرة من السيكونسز. تمام؟ الآن على افتراض إنه إحنا لقينا هاي السيكونسز، كيف بدنا نقارنهم ببعض ونحاول نشوف الفروقات والتشابهات بين هاي السيكونسز. هذا الموضوع مهم جدا، وهو الموضوع الفعلي اللي بيستخدم باكتشاف المسببات الأمراض، وخصوصا إذا كان المسبب جيني، يعني سببه خلل في الجينوم نفسه أو في السيكونس نفسه. وبالتالي احنا بنقارن مثلا سيكونس جاي من دي ان اي سليم مع سيكونس جاي من دي ان اي مصاب بمرض معين، نحاول نقارنهم ونشوف الفروقات بالضبط وين مكانها وشو نوعها وكم عددها. تمام. طيب الحمد لله على سلامتكم. وإن شاء الله تضلكم سالمين خلال الفصل الحالي وما بعده. إن شاء الله بتنتهي الحرب قريبا وبتضلكم أنتم وأهاليكم وأحبابكم كلكم بألف خير. زي ما حكينا بالمحاضرة الأولى، كل الفيديوهات للمساق راح تكون إن شاء الله على اليوتيوب. نفس القناة راح تنعرض عليها كل المحاضرات وما يخص المساق والمساقات الأخرى في جامعتنا. طيب المرة الماضية أعطيتكم exercise number 2. هو إنه to count or to calculate the frequency of some items in two genomic files. One of them was FASTA format and the other one FASTQ format. This is the solution to the exercise. Remember, in this exercise, we ignore everything else except the genomic sequences. So we ignore the header, we ignore the sequencing quality, we ignore the separator, like the plus sign and all those stuff. All right? Okay. Remember in the previous lectures, we were talking about how we solved the puzzle to link all the pieces we got from the sequencing machine to make a full picture out of those individual pieces or randomized fragments coming from the sequencing machine. We use a reference genome as a picture, so we try to match every single piece from the puzzle with this picture and try to link them together so we can build the whole thing after this process. So we never mention about the process that we use to match the piece coming from the puzzle or the sequencing machine with that in the reference genome. So today we'll be talking about this specific topic on how to examine the similarity between the read sequence and each sequence in the reference genome. Remember in Google search, for example, when you type something in the search space and you make some misspelling over there, then the Google search would suggest something that is very close to what you type, but it's in a correct format. For example, if you type computer science, of course, misspell, and then Google search tried to correct it for you and try to ask you, did you mean something like computer science? Should I search for this? Or whatever you type, right? So how does Google search predict that computer science is the correct word? In fact, there are many ways that we can use to calculate the similarity between what you type and what we have in the vocabulary, right? So we calculate how far what you suggest or what you typed and what we should suggest to you as a user, right? And to calculate the distance between one word and another word, we need to use an algorithm that calculates those distances. So today we'll be discussing 3 different methods. The first one called Hamming distance, and then the second one called edit distance, and third way called sequence alignment. The three algorithms or the 3 techniques are used to calculate distances between sequences. Those sequences could be genomic sequences, or it could be anything as a text, right? Or it could be an object. So let's talk about Hamming distance. So Hamming distance is a technique or algorithm that was proposed by Richard Hamming, who's an American scientist who was a mathematician as well, and proposed this algorithm in 1950 to detect the errors when we communicate data. So when you communicate data from one point to another point, we need to figure out whether the data along the way was corrupted or it was as is, right? So we need a mechanism to detect those differences between what we send over a communication medium and what we receive. And that was the main goal of the Hamming distance. And then we could use the exact same concept to genomic data, as we will show in a moment. So Hamming distance is basically the minimum number of substitutions required to change the read into the reference segment. What does that mean? It means this method is able to detect only substitutions, which is mismatches. So when we change a character with another character, think about two sequences. We have whatever character in any location, and would like to change that character into something else, right? That's what we call a substitution or a mismatch, basically. So the algorithm tried to detect the minimum number of substitutions that if we do to one of the sequences, it will appear exactly the same as the other sequence, right? So let's see an example. Probably it will be more clear. Let's have this genomic sequence, and let's see the other genomic sequence. If we compare them, they are exactly the same thing, right? So if we compare character by character, starting from the G and then compared with the G from the other sequence, we find it exactly the same thing. If we compare the T with the T, C with the C, remember in here, the default setting is to have a sequence and another sequence, both of them the exact same length. So that's why we are able to compare character to another character as a pairwise, okay? So in here, since all the characters are exactly the same from the corresponding sequence or corresponding location in the other sequence, then the Hamming distance of those two sequences is basically 0, because I don't need to do any substitution to the second sequence to make it looks exactly the same thing as the first sequence. However, let's see this example. When we have a genomic sequence over here, and we would like to compare it to another genomic sequence where we do ourselves do substitution or those variations. So we have here a T and A, where in the first sequence we have a G and C. So apparently we need to change the T to G, and we need to change the A to C so that this sequence will look exactly the same as the first sequence, right? So in this case, the Hamming distance would be 2, because I need to apply 2 operations over here to make them exactly the same thing. Right, so Hamming distance is very easy algorithm, and it's computed normally in linear time. How we do it in practice, so we need a for loop to go over the two sequences and start comparing the two characters. If they are the same, we don't do anything. If they are different, then we need to add one error or +1 to the Hamming distance that we are calculating, right? And keep applying the exact same thing until we complete the entire sequence. So that's why the calculation or the time complexity of Hamming distance really depends on the length of the sequences, assuming that both of them have the same length. One of the mathematical property of Hamming distance is that when we calculate the Hamming distance between one sequence and itself, we should get 0 because they are the same. And we calculate the Hamming distance for sequence pair, and it's the exact same thing as we calculate the Hamming distance for the second sequence and the first sequence. So it doesn't matter if this sequence is swapped with that sequence. Still, we should have the exact same Hamming distance value. Why is that? Because we are comparing character to character. It doesn't matter if this character in here or that character in here. As long as the two sequences are swapped all together, then the Hamming distance should be the same value. The third mathematical property is that when we calculate the Hamming distance to two sequences and we add it up to the Hamming distance of the second sequence to another third sequence, remember this is first sequence, second sequence, and then we calculate the Hamming distance to the second sequence and the third sequence, then that should give us greater than or equal to the Hamming distance of sequence 1 and sequence 3. You can do some examples and verify the three properties. All right. So when we try to implement the Hamming distance, I already explained this to you, but you can implement it in Python and try to get a working copy or working program for the Hamming distance. So it's a simple for loop, should iterate over the entire two sequences and try to match character to character. If it's not equal to that character or the corresponding character from the other sequence, then we just add the Hamming distance, we increment it by 1. And then we return the distance, and when we wanted to call it or call that function that we have as Hamming distance, we can give it just a pair of sequences. That example is used from this link, so feel free to build it on your own and try to play with it, give it different input sequences. All right? So now let's calculate the Hamming distance between those two genomic sequences. We have one, and we have the other one as in given in this question. Now what we did basically is this sequence is the exact same thing as that sequence, but we add here just an extra character of C. So that little character of C causes a big problem. Why is that? When we try to calculate the Hamming distance between those two sequences, it turns out that we have only two matches, as you can see, the G and G, T and T. But the rest of it, whatever you compare, G and C, A and G, C and A, all of them just mismatch, right? And that gives us a Hamming distance of 7, although what we did was just only adding that little character over there. So how to fix that? That's why we have to use edit distance in some situation. So in edit distance, we don't consider only substitution as in Hamming distance, but in this case, we consider a different type of edits. So in edit distance, we calculate the minimum number of edits. Remember, in Hamming distance, we were calculating the minimum number of substitutions. But in edit distance, we calculate the minimum number of edits. What are those edits? So edit operation could be insertion, so you insert a character, or a deletion, so you delete it, or you delete a character, or substitution, so you change one of the character with another, right? And those edits needed to make the read exactly match the reference segment. That is exactly as in Hamming distance, right? So what we have here, we consider extra edit operation that are insertion and deletions that we don't have in Hamming distance. Let's see an example. So let's consider this sequence and the other sequence as in the previous example. Now remember that we added a C over here. If we add an extra operation over here, which could be an insertion, so we need to insert a character over here or delete the C from here so that this sequence will look like exactly the same as the other sequence. So if we do that, if we do the insertion to the above or the deletion to the down, then we could get an edit operation of 1. As you can see, if we compare A to A, C to C, G to G, C to C, A to A, G to G, all of them would exactly match. And this gives us much more sense than what we have in the previous slide, because we did one operation, but we got 7 and Hamming distance of 7. In here, we could fix that because edit distance allows us to have insertion and deletion. All right, so now let's see more examples. remember, all those distance metrics, not only for genomic sequences, but could be used for any text, right? So let's have here organization and translation. I would like to calculate the edit distance for those two words. So one of the arrangement to calculate the edit distance is try to match every single character and try to arrange it in this way, for example. So we have R matched with the R, A with A, N with N, A with A, T with T, I with I, and O with O, N with N. And the rest are mismatches or some insertions, as you can see in those little dashes. And that gives us an edit distance of 5. Why is that? Because we apply 5 operation to translation to make that as the organization. So we have here one mismatch, that is one operation. We have here an insertion, so second operation. We have another insertion over here, as you can see, that is a third operation. And then we have 2 mismatches, or one mismatch and one insertion over here. So that is 1, 2, 3, 4, and 5. That's why the edit distance in here is 5. If we could consider another arrangement for the exact same 2 words. Let's see. So here is still the same thing, but the difference is in here. Should we add that little dash after the Z or before the I? So if we add it before the I, still works, because when we add the insertion here, so we skip the S and the I and L is substitution, the Z and the dash over here is an insertion. So we have 1, 2, 3, 4, and 5. So still 5 operation. So the edit distance is 5 because we need to apply 5 edit or different edit operation to one of the 2 words to make the to make it exactly the same as the other sequence. Okay. So we could have another arrangement as well, where we apply a match to the R, match to the A, match to the N, exact same as we did in the previous 2 examples. But we could consider, the I and Z as a substitution or a mismatch. If we do that, then the number of operation will be what? Now is not 5, it's 4. Why is that? Let's count it together. 1 over here is substitution, 1 insertion, that is 2 operation, and 2 substitution, so that gives us 4 edit operation. And remember, based on the definition coming from the edit distance, it's about the minimum number of edits, the minimum. So if we find whatever arrangement that has the least number of edit operation, that should be our edit distance. So it's not 5, it's not 5 in here, it is 4. So the edit distance is 4. 5 is wrong because it's not the minimum, right? So 4 is the minimum number. All right? But how we calculate it in real life, how we could guess that those are the arrangement, or this is the best arrangement over those 2 arrangements, how we could calculate that. So let's see an example before we jump into how we calculate it in practice. I have 2 sequences here, Palestine and another Palestine. They are exactly the same thing, so exact match, right? So the edit distance here is 0. Now let's do just single operation. Let's imagine that we deleted the letter E from the second sequence. So Palestine compared to Palestine, right? So there is no E here. Now, when we try to do matches or pairwise comparison, what we got here, 3 perfect match, right? But then here, the E and S, they do not match, right? So a deletion, one deleted character over here causes a left shift of what? Of all those trailing character. We call them trailing character because they are following, or the deleted character was followed by those 5 characters, right? So those are the trailing character, and all of them being shifted to the left direction. So all of them replacing the E character over here. And since that happened, then we want to do the pairwise matches. We cannot use the E to S. That gives us a wrong estimation of the edit distance. Likewise, we cannot match the S with the T, T with I with N. That will give us a lot of mismatches, as we see in the Hamming distance case, right? So if we want to do the comparison, we should do it this way, and which gives us the correct comparison. So S with S, T with T, I and I. And we cannot do the comparison directly as a pairwise because the deletion causes a left shift. Let's remember, deletion causes a left shift. So the comparison should be in this direction. Now, if we consider an addition or insertion, so we have an inserted character to the second sequence. So we have the and sign over here added between the L and E. And likewise, the PAL is compared correctly. So we got perfect match, exactly matching, right? Now, because of the insertion causes a right shift to all those trailing character after the inserted character over here. So we need now to compare in the right direction. So E with E, S with S, T with T, I with I, N with N, and E with E. So when we have a deletion, we compare to the left direction. When we have an insertion, we compare to the right direction. And because we don't know whether it was insertion or deletion in the two sequences, so what we need to do basically is to consider all those cases regardless of whatever the sequences are. In this case, we can consider the calculation for all possible input sequences. So imagine we have those two sequences together now. And now we would like to calculate all kind of shifted version of one of the two sequences. So we fix sequence one as is, we keep it. We consider the second sequence, and we try to calculate all the shifted version of that sequence number two. So what does that mean? Now let me annotate. So think about this sequence. I would like to shift it to one step to the left direction. So what we will get from this sequence is this version. Just exactly the same thing, but just shifted to the left, right? And then we shift it again one more time to the left, one more time, one more time, one more time, and so on. So how many times do we need to shift it? Basically, until the last character over here from this sequence can be matched with the first sequence from the second sequence. So the last character from this sequence can be matched with the first character from the original sequence. In this case, we just stop shifting, right? And how many versions now we have shifted? This is the original one. So we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 9 copies of the original sequence, and all of them are shifted gradually, one by one, to the left direction. Now, that covers the deletion. Remember, in the deletion, we said the deletion causes a shift in the left direction. So that's why we're trying to shift all possible ways, because we don't know whether there has been one deletion, two deletions. If the one deletion, we need only the first one. If two deletions, we need the second one. If 3 deletions, we need the third one, fourth one, fifth one, and so on. So we don't know how many deletions are there in the two sequences. Remember, those two are variables and provided by the user. So that's why we consider all the cases and we shift gradually to the left direction. However, there could be insertion, right? So we need also to consider the other variations which are shifted to the right direction. So in this sequence, we take it as is. Remember, we just fix the first sequence. We don't do any shifted version to the first sequence. We just do it to the second version or the second sequence. We consider that sequence as is, and we shift it by one step to the right direction. So that's exact same thing, but just shifted one step to the right. And we have another copy shifted 2 steps to the right, another copy shifted 3 steps shifted to the right, and so on. So the difference between every copy and another one, the next copy is just one step extra in the same direction. And when do we stop? The exact same thing as we did in the left shifted version. So here, the first character from this copy should match with the last character from the second sequence. In this case, we just stop shifting. And when we consider all those shifted version of the second sequence, now we could match those two sequences in any possible edit operation. Let's see an example that's clear. Now, what we do now, since we calculate all those versions, we try to see when we could match the first sequence with any of all of these versions. So we match this guy, this first sequence, with all the shifted versions, either to the right or the left, or to the original sequence as well, that has no shift at all. So when we try to do pairwise comparison between this and this, we see that there are 3 matches over here, and there are another 3 matches over there, and the rest are mismatches. But when we compare the first sequence with this little sequence over there, we see no matches at all, and then we have 6 matches. We do the same thing with the first sequence to all those copies and try to detect where do they match as a pairwise. So when we calculate this, for example, we highlight only this character because that is the only character matches with this A. We see this A, for example, we go to our sequence in here, we have a G in this location, so it doesn't match. That's why I highlight the orange, which means that those exactly match with whatever we have in sequence 1. All right, exactly the same thing here. We have a G. If we go in vertically to the first sequence, we will see also there is a G here. So that's why we highlight in orange. And now what we do basically is we try just to collect the longest matches that we have all over all locations. The longest matches, as you can see, is this one. So we have 6 matches over here, and that is the longest in all places that overlap with those 6 locations. So if we do 2 vertical lines like this, we will never see anything longest than 6 matches in the same span from here to there. And we will see also 3 matches. If we consider vertically over here, we will see that there are 3 matches over here. And that tells us that we have 3 plus 6 matches between those 2 sequences. And in this case, we could detect that detect the matches between the 2 sequences using edit distance operation. Let's see. Yes, those are the 2 exact matches between the 2 sequences, right? So that was an illustration on how we calculate edit distance in one of the naive ways, okay? Don't worry, of course, this sounds like a bit complex, but I'm pretty sure in the next few slides, you will like the other way to calculate the edit distance. In this way, nobody in practice using this way because it's very laborious. It uses a lot of shift, a lot of making copies of those variation, and you could do a lot of mistakes here and there all over those copies of the sequences. So there is another very nice way of calculating the distance. We will see it in the next few slides. All right. Let me erase the annotation and move on to the next slide. Okay. So what we can see based on whatever we did as calculation in this slide, we can see that Hamming distance is a special case of the edit distance. How is that? You can see that Hamming distance is already included in the calculation because we do calculate the pairwise comparison between the 2 original sequences as they are without any shift. So we just try to compare character to character in here, and then we highlight them in orange. So Hamming distance is part of the edit distance calculation. So that's why we said Hamming distance is a special case of edit distance. All right. So let's see now the way that I mentioned about calculating edit distance in a very efficient way, different from the way that I just showed. So the space of enumerating all possible shifted copies is very huge. Think about a sequence here. So sequence number 1 is million character long. That will give you a lot of enumeration over here, about million shifted copies to the left direction and another million of shifted copies to the right direction. That is a lot of calculation involved. So we cannot afford that naive solution or brute force where we try every single shifted copies of the second sequence and try to match it with the original sequence. That's why we call it a brute force. Okay, so instead we use dynamic programming technique. That is a technique on solving some of the problems that satisfy some of the properties. We're not going to discuss it in details, but we are going to take the example of edit distance on a way or on how we apply dynamic programming to save a lot of calculation involved in this process. So dynamic programming is a tabular computation. It means there's a table should be included in the calculation. And we could use this table to calculate the edit distance, for example, between sequence 1 and sequence 1, or sequence 1 and sequence 2, where we solve problems by combining solution to subproblems. So we solve a bigger problem by dividing it into very small subproblems, and we solve each individually. And then when we have the answer to each subproblem, we try to reuse it. Let's see what happened. And then we try to reuse it to calculate the bigger problem. Oh. Yeah, sorry. Okay. So as I said, we divide the bigger problem into smaller subproblems. We solve each subproblem individually, try to get the answer to that, and then we reuse that answer to calculate the bigger problem. Let's see an example. That is the most efficient way on calculating edit distance, at least compared to the previous way where we enumerate all shifted copies of that sequence. What we do, as we call it dynamic programming, remember, it's a tabular technique. So we need to build a table. The width of the table equals the length of one of the sequences plus 2 cells. So we add 2 extra cells to the length of the first sequence. And the height of that table, or the number of rows, equals the length of the other sequence plus 2 more cells. Okay, and then we add the character of the first sequence in this way. So the first character in third column, fourth column, fifth column, and so on, until we complete all characters of the first sequence. And then we have the second sequence where we have each of the character added to the rows, but still in the very first column. Remember, we skipped those 2 cells both horizontally and vertically. Okay. Now, the edit distance algorithm asks us to initialize the first or the second row and the second column. Okay, so we need to initialize the second row and the second column. How we initialize it? Let's try to annotate. What it says over here, we need to calculate those, which is EI. I mean rows. The 0 here, the column. So column 0, the rows i's, all should equal I. What does that mean? So I have a little index over here, so it helps you to know which column is which. So we call this as 0. This is 1, 2, 3, 4, 5, so on. This is 0, not this one. So not the first cell. We kept the first cell. We call this 0. We call that 0. Okay, this is 1, 2, 3. Okay, so now that is I. So this is I0. So E, this one called E0 and 0. Okay, likewise, this one E1 and 0. 2 and 0, 3 and 0. So that column should fill with the value of I, whatever is I. So in here, we should have 0, 1, 2, sorry, that's 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right? Okay. And in the second row, where we have this equation, so it says E0, that is the row number 0, and column J, so filled with J. So whatever in J in here, we just copy it over there. That is already calculated, which is 0. Then we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right? Let's see. That's the exact thing we did. Okay? Now, the next step in the algorithm to calculate the distance, it says go and check every single character from the two sequences. So go to character I, try to compare it with character J from the second sequence. So if we go to this cell, we would like to calculate it. We go to this character from the first sequence, compare it with this character from the other sequence. So C matches exactly the C from the other sequence, right? So if it matches, then we need to apply this equation. So it says EIJ, which means E1 and 1, so that is the index over here, E1 and 1, right, equals E0 and 0. So we just consider that cell as in here because the two characters are exactly the same thing. So here should be a value of 0, okay? Now let's move to the second, for example, this one. Let's calculate it. So here we would like to compare T and C. So we are comparing T and C. Do they match? No, they are not matched, or what we call mismatch. So T mismatches C. If in case of mismatch, so we need to apply the else branch, right? In else branch, it says EIJ, so here, E1 and 2. So I is 1, J is 2, right? E1 and 2 equals 1 plus the minimum of the three things. What are the three things? This cell, that cell, and that cell. Okay, so the minimum of those three cells, we consider one of them as a minimum, and then we add 1 to it, and that will be the value of our cell. Okay, so now what are these three cells that we need to consider for the minimum value? It is the one above that we are calculating. Imagine you are always in this cell. This is the cell that you would like to calculate, okay? So we consider the cell above it, just above it, and the cell to the left side next to it, right? And the one above it, but diagonally, okay? So that is left upper and upper cell and the left cell. So left upper, upper, and left cell. So imagine I would like to calculate this cell. What should I do? I should look into this cell, and this cell. I find their values. So their values should be calculated in advance, right? And I consider the three values, find the minimum out of those three, and then just add 1 to the minimum, and that will be our value in here. Very simple, right? Let's calculate it for this cell. We said T mismatches the C, so we are in this case. And we said we look into this. Maybe I can use different color. Let's change it into green. So we consider this cell, and this to calculate this one. So we have 1, 2, and this is 0. This is 0, right? So what is the minimum of 0, 1, and 2? Is 0, basically. So we add 1 to it, and that will be the value over here, is 1, right? So now let's see the solution. Let's clear all the annotation. So that is the solution to the entire row, 0, 1, 2, 3, 4. So let's take another example from the same row. How we calculate this one, for example, let's see. We go to this character, we compare it with the corresponding character from the other sequence, which is C. So we compare G and C, they mismatch each other, and then we need to apply that branch, which says, look into this cell, this cell, and that cell. Find the minimum of 6, 7, 8, which is 6. And so we use it over here, and we just add 1 to it as it states in this equation. Okay, very simple. So we can do the same thing to this column and so on. However, because we are going to need one more calculation later on, we are going to save whatever cell that we use in our calculation. What does that mean? So when we calculate the 0, if we use the value in here, then we are going to add arrow. That arrow indicates which value that we uses to calculate this cell. So in this cell, if we uses the value in here in 5 and we add +1 and then we add that value in here, so we need to add arrow this way. That indicates that to calculate 6, we use value of 5, which is coming from this cell. That was the minimum. If this was the minimum, we add the arrow this way. If this was the minimum, then we add the arrow this way. Okay, so all those arrows indicate the direction or which cell that we uses to calculate whatever cell that we are currently trying to calculate. Okay, let's erase all the annotation and let's see all the arrows that we got from this row. So that means, for example, in here, that means I use the value in here and I add 1 to it. So that's how I got 5. Let's continue. What does all those arrows mean? For example, let's see this new one in here, 8. 8, I calculated based on the value of this 8. I didn't consider 7, although 7 is minimum. Why is that? Because if I look into the character over here, it's C. And when I compare it to C, it matches exactly, right? So I don't need to apply the else. I go to the F condition because it satisfies the condition over here. And this tells me, go and just get the value in the left upper cell, this one. So I got this cell over here without adding 1. Remember, it's just applying this condition, right? It's not magic. And that's why I add the arrow in this way, which is diagonal arrow. Okay. Now I continue doing all the arrows. I calculate this column the exact same way I did, and I add the arrows to it. So remember, you don't need to calculate the entire column and then trying to add the arrows. You could do one by one. So when you calculate each cell, you can add the arrow directly to that cell. So in this way, you don't forget whatever you did, right? Remember, the arrows, we're going to mention the purpose of those arrows later on. So don't worry about them now, but we need them later on. So that's why we are trying to build them from now. If we complete the entire table and then we are trying to calculate those arrows direction, it will take us a very long time because we need to guess again, where did we get the value from? And then we could calculate the arrow direction. So it's better to do it now so that we already know which cell we use to calculate each cell. All right, I hope that is clear. Let me clear the annotation, then let's move on. This is how we calculate all those arrows or the values, sorry, in the rows, and then we can move forward with the direction. Remember, as I said, you don't really need to calculate the entire row and then add the arrows. You can calculate one cell on a time and then add the arrow directly to that cell you calculated. Right? And that gives us the entire thing. Let's see any random cell, for example, this guy, how we calculate it. So we go and compare the A from here with the A from there. They are exactly matching each other. So we apply the if condition over here. So what we need to do is just take the value over here and add it in here. That's why the arrow direction is this way and the value in here is 2. However, because we need to calculate 3 cells in advance so that we can calculate this cell, right? We need the upper cell to be ready for us. The left cell, we need it to be ready for us. And the left upper also needs to be ready for us. So these 3 cells need to be calculated in advance. So in order to calculate this, you could go row-wise. So you need to calculate this entire row first, this entire row second, this entire row third, fourth, and so on. Or you could calculate column-wise. So you could start with first column, second column, third column, fourth column. Whatever you do, row-wise or column-wise, you will always be in safe side. So every time you start to calculate, you will see that you always have 3 cells ready for you. If you do row-wise or column-wise, you will always have 3 cells ready for you, okay? So you don't need to worry about it. You could also go diagonally. So you could start with this cell, then this cell, and we can clear the annotation. You could start from this cell, then this and this, this, and this, and then this. So if you start doing it this way, you will also have all the time 3 cells ready for you. Okay, you can try it yourself and see. So you have 3 options. Either you start row-wise or column-wise or diagonally or anti-diagonally. This way we call it anti-diagonally, okay? Or anti-diagonally, okay? This is diagonal and this is anti-diagonal, all right? So now we are able to fill the entire dynamic programming table, okay, using just simple algorithm over here, or what we call pseudocode, okay? However, our goal is to calculate edit distance. So where's the edit distance? I've been calculating this entire table with the aim of calculating edit distance value, but where's the edit distance value among all those numbers? All right, it's very simple. Let's see the demystifying explanation over here. That was tape, sorry. Yeah, so that was the table that we calculate. It just changed the color in the middle, so we highlight some stuff other than the numbers and the arrows. So again, this is your input sequence. This is another input sequence over here, right? And this entire thing we call dynamic programming table. Those index in the top and the left side are just to help you maintain the table. So it's up to you. You want to add them, you want to remove them, it's up to you. It's not necessary, but it will help you a lot. So it's better to have them, right? The arrows, we call them tracking arrows, okay? And the edit distance value, it's always in this cell. It's always in this cell. So we need to calculate the entire table, everything we have here, we need to calculate it to reach this last cell in the corner. And that will be your edit distance value. So it says here, the edit distance between this sequence and that sequence is 2, okay? All right, so I have a little exercise for you guys. So we need to write a Python program that calculates the following: edit distance for any 2 input sequences, dynamic programming table, and a table for tracking arrows, The hint we have here to help you, you can represent each arrow direction using a unique number. What does that mean? So if you find it difficult to represent those arrows, right, the diagonal and the down arrows, you can replace them with numbers. So this is the dynamic programming table, and this is, you could use another table. You don't need to add the arrows to the same table over here. If you could do it to the same table, that will be very nice. But if you find it difficult and complex, you can build another table and just fill it with the arrows that you have, right? And even if you find it complex to add the arrows to the table, you could replace them with the numbers. So you could indicate this arrow with 0, this arrow with 1, and this 2. So you need to have a table, that is the dynamic programming table, and another table where you have the arrows, or what you have the numbers instead the arrows, 0, 1, and 2s, okay? So in having distance, I already provide the Python code to you. In edit distance, that is an exercise for you. It's a very nice exercise. And it's in Python, so you won't suffer. So I hope you enjoy this exercise. And we will see the answer next lecture. Okay. So now we already know how to calculate the edit distance using the edit distance algorithm, using dynamic programming table. But how about the type of each edit operation that we did? So now we know that we have 2 edit operations needed to be applied on one sequence to make it looks the exact same as the other sequence, right? So, but what are those 2 edit operations? Should I do insertion? Should I do deletion? And also, what is, or where should I apply those edit operations? So the location of every single operation I need to apply. Should I apply to the first character, second, third, fourth, and so on? So that's a very important question. So with that, we need a step, a computational step that is called backtracking. Backtracking. This is another step, but we have to do it right after we calculate the table. So the first step is to calculate the entire table, okay, with the arrows, all right? And when we arrive to the last cell, what we do backtracking. Remember, we have a tracking arrows. So now we need to do the backtracking. What does backtracking mean? Let's go back to the previous slide. Do you remember the slide? We said this is the edit distance we have. Do you remember this slide, right? We said this 2 is our edit distance. So now backtracking says we need to track every single cell, how we get it. So how we got this edit distance value 2. Based on the arrow I have in here, right? It says I got it from this one, okay? So I back or flip the arrow. The arrow, I have it this way. So now I flip it in this direction because I'm doing backtracking. Instead of going from first cell down on the road, I'm doing it from the last cell upward, okay? That's why I call it backtracking. Remember those, we call them tracking arrows. Now I do backtracking or reverse engineering, reverse step, okay? So I reverse this arrow to go to the left direction. And now this cell, how we got it? We got it based on this arrow from this cell. So now we reverse this arrow to indicate this direction. And then this one, I got it from this cell. So I reverse this arrow this way, okay? Now how I get 1? I got it from this cell. Now I indicate the arrow in the opposite direction, this way. How I get this 1? I get it from this one or this cell. So the arrow should be reversed into this. So you see, I apply or I calculate the blue arrows. It helps me a lot. Now everything is ready for me. I don't need to calculate the arrows from scratch. They are already ready. They are telling me that this cell was calculated based on that cell. So that's why now the arrow is flipped this direction. Likewise in here, this arrow coming from this. So I flip this, I reverse the direction of it. And now in this cell, as you can see, the arrow direction is coming from up to down. So it was based on this cell, not this one, okay? Not the one, it's coming from the 0. And the arrow is indicating from the top to the bottom. So now I reverse the direction of it. It will indicate going from bottom to top, okay? So all those reverse direction of those arrows, I call it as a backtracking step. That is a backtracking step. So if I ask you to define what is backtracking step, it's a step that I use to calculate the location and the type of every edit after I calculate entirely the dynamic programming table. So I go from the last cell over here and I track based on the tracking arrows where which cell I was using to calculate this cell. So from 2, I was in 1. From 1, I was in 1. From the other one, I was in this one. From this one, I was in this one. And I always reverse the direction of the arrow. So let's see it. If you go back to this is the solution, basically, much cleaner version of it. So I have the 2 in here. It's coming from this cell. So I have the arrow coming from here. The arrow previously was indicating or has the direction from left to the right. I reverse it, and it's now from the right to the left. Okay, and based on this cell, should go to the diagonally in here. Previously the arrow was this way, so I reverse it. Now it's becoming this way, this way, this way, and so on. And if you remember that arrow coming from top to down, now it's going from bottom to the top. Okay, and I keep doing this until I arrive the corner of the table. So what does that mean? What does everything I did here mean, including the arrows that I reversed the direction and the yellow highlighted cells? If you look carefully to it, you'll see that I'm trying to build the alignment between, or what we call the arrangement of the edit operation between the two sequences. What does that mean? So it means if you look carefully to the meaning of those two cells in here, so I have this cell means substitution, this cell deletion, and this cell means insertion. So when I calculated this white cell over here, if I was using the value from this top or upper cell, it means the operation I should apply is insertion, as indicated here. But if I was using the value from the blue cell, then the operation I should apply was substitution. Okay. If I need to use the value from this pink cell, then the operation I should apply deletion. Okay. So if I clean now the annotation and I look carefully to what I have here, it looks like all these 4 cells I was using from diagonal shape, the upper cell, right? If I ever use those, it means either substitution or exact match, either substitution or exact match. So based on this, if I see, for example, C and C, it's exact match, T and T exact match, C and C exact match. So everything over here was exact match. It could be substitution as well. If substitution, then I will have an increment of 1 over here, an increment of 1. Okay, so if I don't have increment 1, it means exact match. So I have CTC, CTC exact match. That's why I add these 3 vertical bars to indicate that this exactly matching with this. Now remember, if I always go diagonally this way, then it means substitution of or matches. But I don't go diagonally. I don't continue diagonally after the 0 in here. Let's see it clearly. So this is diagonally, right? In here, I stop going diagonally and I go down. If I go down, what does that mean? It means I have insertion. If I go down, then it means I have insertion. That's why I insert 1 character over here. This character doesn't matter which one, A, C, G, T. That's why we add dash here. Doesn't matter, but still inserted character. Because I go based on the backtracking path that I have, I go from up to the down, right? That's why I have inserted character over here. And now I have a space because I cannot match the inserted character with a T because I don't know the character in advance, right? Remember, this cell doesn't have any meaning, right? We just added up. There is no character here and here. So when we count 4 zeros, it's in fact 3 zeros, 3 matches, right? So this cell's just ignore. Doesn't mean anything. We have only 3 matches over here. Now we go down, insertion. Now we continue diagonally. Diagonally, what does it mean? It means either substitution or matches. Either substitution or matches. If we continue diagonally again after that insertion. So if we look carefully, we will find like The next character is A, so all of them exactly match, right? That's why the value here is still 1 all over those places. So 1, 1, 1, 1. What does it mean? It means here zeros, no edit operation was happening. So all of them exact match. But now the moment we did insertion over here, we start incremented from 0 to 1. So that's why we have now 1 insertion. But in the next character, it's exactly matching each other. So we don't need to add anything. It's still 1. Likewise in here, still 1, 1, 1, 1, and 1. All of those means exact match. So we have 1 here, 2, 3, 4, 5, and 6 character. So we have 6 operation as exact match. Let's count them. 1, 2, 3, 4, 5, 6. That is exactly 6 operation. There is no change, no substitution. That's why the number is still 1. The first one over here means that there was insertion operation. That's why it's incremented from 0 to 1. Okay. Now we still have the last cell because this is not the edit distance. This is the edit distance. And when we go from left direction to the right direction, right? When we go from here to here, it means deletion. So I have a deleted character. So I have a deleted character. And that deleted character means I need to delete a character from this operation. So when we insert in here, and we could delete this G to make it exactly the same thing, or just insert character from the other sequence as in here. So either you delete from here, that will make it exactly the sequence, exactly the same as this, or you insert to the other character as a dash over here. It means that this character cannot be matched with this. That's why we add character over here. I hope it's clear how we got from backtracking to the arrangement of edit type and edit location. Edit type and edit location. So if I ask you to calculate the edit distance, you calculate this dynamic programming table, and that value in the corner over here, it is the edit distance value. If I ask you also to find the location and the type of the edit, you need to apply, after calculating the dynamic programming table, you need to do backtracking. Backtracking, again, we said, we go to this corner cell, and we try to flip all the arrows that send us to this value. So we said, we ask ourselves, how we calculate the value of 2, it's from this cell. So we reverse the arrow coming from this. How we calculate the value of this one, we calculate it from this cell. How we calculate this value, we calculate it this way, and so on. And every time we reverse the arrow until we reach the end of the table. And then we do reverse engineering to this legend over here, okay? This means, again, substitution or match. Substitution or match. That's very important. You could also look it up from the pseudocode we have in here. If we delete the annotation, you can see this one is already included and this one. This means mismatch and this means exact match. That's why we consider this cell as substitution or exact match. Okay. Let's go back in here. All right. I hope it's very clear. Everything, I believe, will be much more clear with practice. So you need to give yourself some exercises or homework and try to solve it yourself. Give yourself whatever random sequences over here, try to build a dynamic programming table yourself. Okay? All right, so let's continue with edit distance. Now I have another question over here. I would like to calculate the distance between organization and operation. So one of the arrangements is to do it this way. The other arrangement is to do it that way. And if we check the number of operation we do here, 1, 2, 3, 4, 5, 6, 7. That's 7 operation. How many operation we did here? 1, 2, 3, 4, 5, 6, 7. That is also 7. So we have 7 operation and another 7 operation, but they are totally different arrangement. So which one to consider? Should we consider this one or that one, right? That's a very important question. If we end up in having two solutions to the same question, what should we do? In this case, it's better to use what we call sequence alignment. Sequence alignment. So I already give you example on when to use Hamming distance and when to use edit distance, which is very important when we add insertion and deletion to the edit operation allowed, right? In Hamming distance, we only have substitution. We don't have insertion or deletion. Likewise in here, when we have multiple arrangement and we don't know which one to pick, we could use sequence alignment instead of edit distance. Let's see example. All right, let's clear the annotation and start with sequence alignment. So sequence alignment is a way that we can generalize edit distance. So that makes an edit cost dependent on where it is applied. So now it's important to consider the edit cost. In the edit distance, we don't have edit cost. We penalize everything as one, right? All the mismatches, insertion, deletions were penalized with one. Now we will add a new term to the operation. We call it as edit cost. So each edit operation could have a different cost. Each edit operation in sequence alignment could have a cost, okay? Now, we will take one example, one algorithm as an example called needleman-wunsch. Needleman-wunsch. Needleman-wunsch, okay? That is the name of the algorithm that we are going to study. However, this algorithm is coming from this paper. This paper was proposed in 1970. Yes, it's a very old paper. However, it's still state of the art. Everyone is using it currently. There are different variations of the algorithm, much faster, okay? But still, there are a lot of tools that use this original algorithm, okay? The tool is coming from the author's last name or surname called also Needleman-Wunsch. So that's how we come up with the name of the tool, okay? Needleman is one author, Wunsch is the other author, and combined called Needleman-Wunsch. All right, let's see example. So as a definition, it calculates, Needleman-Wunsch algorithm calculates the best arrangement of matches and edit operation. What type of edit operation? We still have the exact same as in edit distance, which are insertion, deletion, substitution. Those needed to make one sequence exactly matches the other one using the highest scoring path in the dynamic programming table. Remember, now we have a scoring scheme for the dynamic programming table. So each edit operation will have its own cost, penalty, or a cost, okay? In edit distance, we don't have those. So edit distance uses a unit score. So in edit distance, each edit operation has the cost of one or penalty of one, okay? So all operations are penalized equally with one. We also call the edit distance as Levenshtein distance. Levenshtein is the surname of the author that proposed this edit distance operation. Okay, so we call it Levenshtein distance. Let's see how we have different costs and sequence alignment. So in Needleman-Wunsch algorithm, the pseudocode is a bit different in here. So the initialization, we fill this with 0 as an edit distance, right? However, when we fill this row, what we do, this row means the row number 0, and the J is the column, right? So this is the equation that we are going to use to fill this row. It says J times G, J times G. The J is the index we have over here. So 0 times G, which is 0, basically. That's why we have it as 0 in here. 1 times G, so that is G. This is 2G, 3G, 4G, and so on. But what is G? What is the value of G? G is the penalty or the cost for gap. A gap is a term we use to indicate insertion, or deletion. Okay, insertion or deletion. So if we have insertion or deletion, we just call it a gap. And the gap, we have a penalty for it called G. So it's up to the user. You can replace G with, for example, 4, or you can replace it with -5, or you can replace it with -10. Okay, that is a cost we give it, or penalty we give it to the insertion or the deletion. Okay, so this is 2 times 4, for example. Then we replace 8 over here. 3 times 4 is 12. 4 times 4, 16, and so on. Now let's look into the second column over here. Let's try to calculate this column. What it says, look in this equation, right? I0. I is the row, which is in here, and 0 is the column. So I want to calculate this column. So it says I times G. I times G. I here is 0. 0 times G is 0 again. 1 times G is G, right? 2 times G is 2G. 3 times G is 3G. 4G, and so on, okay? So the G here is still the same thing. Whatever I use for the insertions, I'm going to use it for deletion, okay? Remember, this direction is deletion, and the one above is insertion. So if I'm here, this one consider insertion, this one consider deletion, okay? So whatever cost I use for insertion, I'm going to use it for deletion, okay? So that is 4, 8, 12, 16, and so on, and continue, okay? Now that is easy for initializing this row and that row. I cannot use initialization for the other rows. I just use it for this row and that row. That's why I fixed this as 0 and that as 0, okay? Now for the other rows, let me clear the annotation, make it clear. So I assume I calculate this row and calculate this column. Now let's go to fill the other cells. Imagine I'm here. I need to calculate this cell. What should I do? It's still the same legend. That means I need to look for this cell, and for that cell, the exact same as I did in edit distance. However, there are differences. In edit distance, I have value of 1 plus min. That means 1 plus the minimum of those 3 cells. Here, I don't add the 1. The 1 was a penalty cost for all the operation, which are substitution, insertion, and deletion. I don't have it, and I don't have minimum. I have maximum for needleman-wunsch, okay? And then I add a penalty, depends on the operation itself. And I add penalty, depends on the operation itself, okay? What does that mean? It means I need to find the maximum of this cell, okay? This cell means what? Substitution or matches. So either I add M for matches penalty or substitution. So that's why I have 2 duplicated terms here. This means the left upper cell, this one, the blue, plus a match cost. Again, this depends on the user. So the user can define G, M, and S. Just give it any value you want before you fill the table. You can say G equals 4, as we did previously. M equal 8, for example. Substitution equal 3, okay? Could also have negative value. So you could have a -3, -4, and +8, okay? So we add the penalty, whatever we have here, to the value of that cell, right? And we add the S to the value of that cell. Now we have 2 values here. We also consider this one, and we add insertion penalty, which is the G. We also consider this cell, and we add the deletion penalty, which is G, the gap, right? And then we find the maximum of those 4 values. The maximum of this plus G, the maximum of this plus G, maximum of this plus the S, and this plus the M. So the maximum of those four values will give us the value of that cell, okay? It needs some time to focus on the pseudocode. Do some calculation over here with your hand. Try to calculate it based on those three cells. Try to track whatever we have index over here for the matrix, and then you'll get it correct. Make sure this is the penalty for matches, penalty for substitution, penalty for gap, which is insertion, and or this is deletion, and this is the gap for insertion, as you can see in here, okay? In edit distance, we don't have any penalty for the match. This is 0, right? In edit distance, the gap for S is 1. The penalty, for gap is 1. The penalty for gap is 1. The penalty for substitution is 1. The penalty for matches is 0. We don't have it, okay? And in edit distance, we have min operation, but in needleman-wunsch, we have max operation, okay? Maximum. Remember those differences between the edit distance and the sequence alignment. All right. So I will have this as another exercise for today. You need to fill the previous table. It's very easy. I already started with it, so you can continue. Remember, you always need to show the tracking arrows. You need to show the tracking arrows while you are calculating. Exactly the same thing as we did in edit distance. If you reach in this cell using this cell, just add arrow this way. Or from this cell to this cell, just add arrow. From this cell to this cell, just add arrow, okay? Remember to add those arrows on the dynamic programming table. It will help you a lot when you do backtracking. In edit distance, we said this cell is the edit distance value. In needleman-wunsch, we say this cell is the alignment score, the maximum alignment score, or the optimal alignment score. So in edit distance, again, we say this cell is the edit distance value. In needleman-wunsch, we say this is the alignment score. Maybe I can write it for you. Alignment score. Alignment score. Okay. So this is the alignment score. This is alignment score, alignment score. And when we do backtracking, imagine this cell coming from this cell. So we reverse the arrows as we did exactly in the edit distance. And then we call this as optimal alignment path, optimal alignment path. So the arrows that we use to reach to this cell, we call them the optimal alignment path. So that the backtracking in here is exactly the same part as an edit distance. That's why I'm not going to show it, okay? It's the exact same part of edit distance calculation. We call this path as alignment, optimal alignment path, and the value in here, we call it alignment score. Okay, so that's an exercise for you. Now let's see a very important topic that's called optimization. Optimization, okay? So, yeah. Optimization. So now think about the dynamic programming table that we built, right? So the width of the table was based on the length of the sequence we use here, and the height of the table was based on the sequence used here. So think about the sequence length over here was 30,000 character, and the sequence over here also 30,000 character. So how many cells we need to calculate in the dynamic programming table? It's basically 30,000 times 30,000. And that will give you the number of cells that we need to calculate in here, right? That is basically 900 million cells, or byte, assuming that each cell fit with 1 byte, okay? 900 megabyte. That's a huge, that is really huge. Think about sequences that is 300,000 that will give you about 90 billion byte. That's a huge, very huge table, and may not fit in any of your DRAM. Most of your DRAM, right, in your laptops or computer, it's about 8 gig of byte. So that will cost you a lot. So your software or whatever tool you are building to build this table, it will going to take weeks to complete. Okay, so that's why we're going to give you 2 techniques to optimize the algorithm, makes it much faster, reduce number of cells. The first way, or the first technique to do that, called banded edit distance. Banded edit distance, okay? It calculates only the cells that are within a parallelogram, which is this shape. Parallelogram is this way. Okay, that's what we call a parallelogram, which is similar to rectangular, but we make it like italic, okay? Or we shift it to the left direction. That is a parallelogram. So we calculate cells within a parallelogram that has a width of 2b, 2 times b, where b is an integer number specified by the user. So b is an integer number, and the width of the parallelogram is 2b. The number of diagonals vector is 2b plus 1. What does that mean? It means if I want to calculate the width of the parallelogram here, I go to the corner, I consider this as one diagonal, okay? I consider this as one diagonal, the corner, and then I count b number of diagonals to the right. This is 1, this is 2, and this is 3. That will give me b to the right and b to the left. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. That is 7 diagonals, which is 2b plus 1. That is the number of diagonal vectors that I need to calculate. So I don't need to calculate basically everything in this area and everything in this area. I don't calculate it. So I stop at the moment I reach 2b plus 1 as the number of diagonal vectors, or the width of the parallelogram should be 2b. What does that mean? It means whenever I go this way, I count how many cells I have. 1, 2, 3, 4. So that in this example, I have or the width of the parallelogram, which is this way. You could consider it as this is the main diagonal, right? And then you count 3 diagonal vectors to the right, 3 diagonal vectors to the left, or you could consider counting this way in each row. So this is the main diagonal, and this is 1, 2, 3, and this is 1, 2, 3. Okay, this way you're always going to calculate 2b plus 1 diagonal vectors. Okay, so that's why we said b is somewhere between 1 and the length of shortest sequence. If b is 0, it means I'm going to calculate only the diagonal vector, right? That is going to give us Hamming distance, because at each of those cells in the diagonal, I compare this character with the corresponding character from the exact same location in the 2 sequences. That is Hamming distance, basically. So what I need to do, basically, is going to the table, okay? Let me clear this again. Going to the table, find the diagonal path, and then calculate 1, 2, 3 cells and say, I'm going to calculate only those cells and 1, 2, 3, and I'm going to calculate only those cells. Or you could go to the row-wise this way and say, this is my diagonal. I'm going to take 1, 2, 3 from here, 1, 2, 3 from here. And remember, the value 3 from here and 3 from here is based on b. So it's up to the user. If you want to specify b as 4, what you need to do is the exact same thing. You take the diagonal in the middle and count 1, 2, 3, 4. So you take this cell's included. 1, 2, 3, 4, this cell is included. In case of this one, for example, this is the main diagonal or the middle. I consider 1, 2, 3, 4. So I take this cell included, but 1, 2, done. I have no more cells here to include, so I just exclude them and I consider only those two cells to the left direction. That is fine. Okay? All right? Okay. It's very useful when the optimal alignment is guaranteed to be found if it has at most b edit. So as you can see from the blue tracking, this is the blue tracking, this is the edit distance value. So if we go, how we come to 5, we're coming from this cell to this cell, and this cell, this to here, this to here, here, and so on. So this blue line is the optimal alignment, okay? Or the optimal solution, optimal arrangement for edit distance, all right? If this blue does not exceed this area, then the banded alignment is very useful. However, if the blue should go this way, then if your band is very small value, you are going to underestimate the edit distance value. So your edit distance value will be wrong. The 5 here will be wrong if in the original complete table, your optimal arrangement or the blue line is exceeding the bands. If this blue line is coming, let's make it the blue. If this blue line is coming this way and then this way, based on the arrows that we have, and then this way, then band of 2 doesn't work for you. It will provide you wrong calculation for banded edit distance, okay? You need to increase the band. You need to use, for example, 10, B of 10 or B of 20. So you need to include 20 cells from right and 20 cells from left, and then the band or the arrangement that you arrive or the backtracking, it's already included in this shaded area. Okay, I hope this is very much clear. This is really important on how you choose the value of B. Okay, so it depends on how many edits you expect to have. If the edits is 5, then you would expect your calculation or backtracking to be within this 2b plus 1. Sometimes it depends. If you have a lot of insertion, then you'll see your blue line is coming this way. Okay, every time you add insertion, then it will be shifted like this, again shifted like this, shifted like this. So you'll see it quickly coming outside the shaded area. Okay. Again, this will be much clearer with examples. So you have to do a lot of example for this. Right? Right. So yeah, I hope this is very much clear on banded edit distance. So I'm going to give you some exercise on this. So you'll see it at the end of the lecture. But you can see the huge difference in calculating the edit distance as a complete dynamic programming table and also as a banded edit distance. So you can see the number of the diagonals that you need to calculate is only 2b plus 1, 2b plus 1, where b is integer value specified by the user. Could have a value of 0, but that will be Hamming distance, not edit distance calculation. So that's why we said b somewhere between 1 and the length of the shortest sequence. Okay. All right. So this is the paper where they propose banded edit distance. You can see this paper also is old. It is proposed in 1985, but it's very fundamental. It's still used until today. So that is the beauty of proposing something really useful, and people could use it for hundreds of years, basically. All right, let's see the second method on optimizing the way we calculate edit distance or sequence alignment. The exact same method could be applied to sequence alignment, could be applied to edit distance. Same thing with the banded operation. In this technique, we call it adaptive banded, adaptive banded. In the first one, we call it banded. In this one, adaptive banded. What does it mean? Let's see. It calculates only the cells that are very close in value to the minimum score in each row. So if you consider any row, okay, what is the minimum in this row is 2, okay? What I would like to consider as a close value to 2, do you want to consider 3, 4, 5, 6, 7? So here in this example, they consider 3 as the closest value to the 2, right? So they calculate the cell to the right, they find the 3. Is 3 close to 3 or 2? Yes. How about they calculate the next one? They find it 4. 4, it's not close to 2. It depends on how you define very close. So in here, they define it as the min plus 1. Okay, this is the equation that we are going to use to fill this table. So we start in any cell, for example, we start always from the top. So we calculate 0, 1, and 2 as initialization, right? And then 1 and 2 and 3 as also initialization. And then we start calculating from here, right? Let's use green color. Let's make the font a bit bold. Okay, so we use 0 here, 1, 2. What is the minimum in this row, entire row? So we need to consider the initialized value of 1 as well. The smaller one is 0, right? So now 0, is it within the range of 0 plus 1? Yes. So how about 1? Is it within the range of 0 plus 1? Yes. How about 2? No. 2 is greater than 0 plus 1, which is 1, right? So 2 is greater than this value, then we ignore the 2. So this we don't need to consider. So we consider only 1, 0, 1. Now we go to the next row, same way we calculate the 2 is already there from initialization, right? So we calculate the 1, 1, 1. And while we are calculating, for example, when we calculate the 1 over here, we say we have now 1 and 2 in the same row. Which one is minimum? 1, right? So is 1 within 1 plus 1? Yes, it's still less than this, okay? Or less than this, okay? So 1 is less than 1 plus 1. Then we continue calculating the next cell is 1. 1 is still less than 1 plus 1. 1, 2. 2 is still less than or equal 1 plus 1, okay? When we move next to the 3, yeah, we find that 3 is already exceeding the minimum plus 1 equation. So we don't include it, we exclude it, right? So likewise, we keep doing this all over until we calculate the edit distance value over here. If you see, the big difference between adaptive and banded is what? Is that we don't have a fixed number of cells to the right side and left side, okay? So you can see here, for example, in this row, we have large number of cells over here. But in this row, for example, we have smaller number of rows. And here we also have smaller number of rows. So if you count the number of cells in here, 1, 2, 3, 4, 5, 6, 7, 8. We calculate it in here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 cells over here. We have 9 cells. We have 8 cells, we said. Yes, 8 cells over here, right? So you can see the cells are different along the solution or the backtracking, right? And that's why we call it adaptive. So we adapt the number of cells in each row based on the value or the score in the cell. So we calculate the boundaries of the calculation is here. It depends on the minimum plus a value that is based on the user, and we give it a name here as A. So the user specified the A, the minimum, we don't know it, we cannot know it. We have to start calculating the value in each row to know the minimum value. But A, you can assume it or it's given in the question, okay? So that is what we call adaptive banded edit distance. It's very useful compared to the banded because we adapt the number of cells to be built based on the optimal alignment path instead of a fixed number. So we don't fix the number of cells to the right and left. We adapt the solution based on the path. Whenever the path is going right, then we don't need to worry about coming out the shaded area as we see in the banded edit distance. So if the path is going this way, you will see the calculated cells will be always around the backtracking path, right? And this way, we really need not to worry about the path, but still we need to determine the best value for A, okay? And that's also, as you can see, leads to larger speed up and storage saving compared to the banded because we calculate much less number of cells compared to the original edit distance algorithm. All right, so I hope those two techniques give you some idea on how we could optimize the calculation in the edit distance. Still, there are a lot of algorithms proposed even this year to optimize the number of cells that we need to calculate in the edit distance. So I would say this is an open problem until now. This is the paper that proposes the adaptive banded. It's introduced in 2018 from Suzuki and Kasahara. Those two researchers who I visited in Japan are doing a great job. But you can see there are many other algorithms that were proposed recently even. One of them, the banded over here, you can see that always the band has a fixed width of the parallelogram, right? But there are other algorithms that you can see the number of calculated cells. So for each of those algorithms, basically a table, right? There is a dynamic programming table, this shape, right? And there is also for the next one, there is this dynamic programming table is this shape. So this is the calculated area only. As we move to the edit distance solution here in the corner, you can see that we reduce the number of calculated cells. So this heat map is just try to mimic what we have as the number of calculated cells all over here and here. In this algorithm, okay, this is the dynamic programming table. Now, let's make it more perfect. This is the dynamic programming table that we are trying to build. So this provides the least number of calculated cells. So each of those algorithms try to propose different mechanism, different optimization technique to reduce the number of calculated cells. If you are interested, feel free to look into those names. You will find different algorithms and try to understand how it works. We also give a comprehensive overview of this algorithm in our paper in section 7.3, accelerating sequence alignment. So have a look. In our paper, We also go over multiple of those algorithms, including needleman-wunsch, but also smith-waterman and many other algorithms. And now it's time for the quiz. So I'm going to assign you the first question in the slides. So I'm asking you to generate a genomic sequence that is randomly generated using this tool, online tool, and then making another copy of whatever you generate in here. In the first point, you generate a sequence of length 15. Then you copy that sequence as is and try to perform yourself edit operation. So you try to do 2 insertions, 1 deletions, and 2 substitutions. So that is 5 edit operations. So you need to do 5 edit operations to the sequence. And sorry. So you need to do 2 insertions, 1 deletion, and 2 substitution anywhere in the sequence. Imagine this is your sequence, A, C, G, T, something, right? It's 15 character. You just make another copy of it, A, C, G, T, A, right? It's another 15 character. And then try to delete, for example, C and T, or sorry, it's 1 deletion only. So you try to delete only 1 character, try to insert 2 character, for example, T and T somewhere, and then try to make substitution. For example, this one, change it to C, this one, change it to G, okay? Just try to make randomly anywhere, but please pay attention to the number of operation that I ask you and the type of operation, okay? And then at the end, after you finish all your operation, consider only the first 15 character from the second sequence, because you add some characters, so you might have extra character here, or because if you delete some characters, you have less character, so you could fill it with some dummy data, okay? But make sure you consider only the first 15 character from the second sequence. So you will have 15 character in here, 15 character from there, okay? Now you need to apply the edit distance algorithm to your sequence pair. Try to calculate the edit distance using the original method, which is the dynamic programming table, the complete table. You need to calculate it, which is 15 cells times 15 cells. That's the whole table, okay? Now you need to calculate also the types of each edit operation and the location of each edit operation. That is the backtracking. And you need to show your work and all your steps, okay? That is the first question in the quiz. In the second quiz question, you need to apply the first optimization technique, which is banded edit distance technique. You need to optimize the number of calculated cells, and choosing the value of B is up to you, but try to use an appropriate one, okay? Try to be wise when you choose the value of B so that your backtracking won't be outside the shaded area or the parallelogram. You need to show your work and when you rebuild the banded DP table. You don't need to do backtracking in here, just build the dynamic programming table and show me the solution, okay? And the third question, let's say, so this is number 2, and this is number 3, third question. You need to apply now adaptive banded edit distance where A equals 2. A equals 2. So you need to find the minimum yourself and try to have all values within the minimum plus 2, okay? To calculate the edit distance for this. Now, you need to tell me how many cells would be calculated using adaptive banded edit distance, and we would like to compare it between the banded and the full dynamic programming table. So you will have number of cells for the full, for the banded, and for the adaptive banded. However, be careful here, the excluded cells that you calculate their values still contribute toward the final count. What does that mean? If you remember in here, if you remember that we need to calculate these cells to know if it is within the minimum plus A or not, right? So or is not within the minimum plus A in this row, so it's excluded. However, you already calculated, so we need to count that in the total number of count of how many cells you calculated, okay? So all of those cells are in the number of cells that you calculate, although they are excluded from the shaded area or from whatever you consider for the backtracking, okay? I hope those 3 questions are clear, the quiz. So good luck for it. I'm going to send you a submission link soon in the group that we have so that you can submit your solution to these 3 questions. All right, I hope you enjoyed the lecture for today. I hope we learned something new out of it, how we can compare the 2 sequences, whether they are genomic sequences or just text, how we can figure out the optimal number of differences, the type of those differences, and the location of those differences. We learn about Hamming distance, edit distance, and sequence alignment. We also learn about 2 very famous optimization technique on reducing the number of calculated cells in the dynamic programming table. First one called banded, the second one called adaptive banded. All right, so we will meet again next week with the next lecture. It will be on pre-alignment filtering, very interesting topic. And hope you will stay safe and see you next week.